Now to how to calculate the required output capacitance value in a buck converter. So first of all, what is the current that's flowing in the capacitor? We mentioned before that this current is periodic, so we can get its Fourier series and find that it has a DC component and then high order harmonics. And so on. So we mentioned that for DC, since the filter, the LC filter or RLC filter is basically a linear network, so we can apply KCL at each harmonic component. At DC, the capacitor is open circuit, so basically all of the DC component will flow into the load resistor. On the other hand, for the high order harmonics, for the harmonics from the fundamental to infinity, we'll find that all these harmonics will see both the capacitor in parallel with the load resistor. And if we assume that 1 over j omega c is much smaller than the load resistance R, then all of these harmonics will flow into the capacitor. And so we can say that the current that's flowing into this capacitor is basically the inductor current, just remove from it the DC component of the inductor current. So basically all of the harmonics in the inductor current flows into the capacitor and none of the harmonics flows in the load resistance. That's of course assuming 1 over j omega c is going to be way less than the load resistance R, where omega is the frequency of the fundamental. Okay. So as you can see, the inductor current, its DC component flows into the load resistance because the capacitor at DC is open circuit, while its harmonics flows into the capacitor. And so the capacitor current, as I just mentioned, is the inductor current, just removed from it is DC component, which is the output load current I out. And basically the inductor current looks triangular as shown in this figure, with a peak to peak value of delta IL. Now, if we look at the capacitor current, we see that it has positive portions and negative portions. So these are positive and negative. The other one is negative. So what's positive current? Positive current means current that's being injected into the capacitor. So all of this current, all of this triangle gets injected into the capacitor. And what will happen to the voltage across the capacitor? Well, the voltage across the capacitor at this point had a minimum value. And after this triangle that got injected, all of this charge that got injected into the capacitor voltage reaches its maximum voltage value. On the other hand, for the negative values, this negative triangle, this negative triangle represents current that's taken from the capacitor, and so the capacitor voltage moves from its max value to its minimum value. Okay, and periodically repeats. Okay. So at the zero crossing of the capacitor current, you will find the capacitor voltage at its minimum and maximum values. Now the question is, how does the capacitor voltage changes between its minimum and maximum? Does it change linearly as a straight line? Does it change sinusoidally, or in what waveform does it change? Well, that's easy to determine, since the capacitor current, the current flowing into the capacitor, is equal to the capacitance C times the first derivative of the voltage across the capacitor, which is dV out by dt. Right? Remember the buck converter. I have a capacitor, then the load resistor R, C, and the voltage across the capacitor is basically the output voltage. So the current in the capacitor is C times dV out by dt. Now, if we bring C to the other side, we'll find that the first derivative of the voltage across the capacitor is equal to the capacitor current divided by C. And so the slope of the capacitor voltage is basically determined by the current flowing into it divided by C. where c is just a constant number. So what function has a first derivative that's linear, straight line? Well, if you have a function that's kx squared, then its first derivative would be 2kx, which is a straight line, a straight line with a positive slope. On the other hand, which function has a straight line with negative slope is, say, minus kx squared, because its first derivative will be minus 2kx, a straight line with a negative number, straight line with a negative slope. Kx squared looks like u character pointing upward. On the other hand, minus kx squared look like u character pointing down. So now at this point, this is a minimum, maximum value. As we said, all of this is charge being injected, so it will take the capacitor voltage from its minimum value to its maximum value. This represents charge that's being taken from the capacitor, so essentially the capacitor voltage will move from its max to minimum and so on, repeat. And then at this point, the capacitor current is a straight line, so the capacitor voltage waveform will be a quadratic function. And since the slope of the line is positive, then the quadratic function will be pointing upward, u pointing up. On the other hand, during this interval, here the capacitor voltage reaches maximum value, while this is a straight line with negative slope, so the capacitor waveform is just a quadratic function with, essentially a u pointing downward, and so on, u pointing upward, u pointing downward, I just connect between them, and so the capacitor voltage waveform looks like this. As I mentioned, here it's a u function, quadratic function pointing upward, here is a quadratic function pointing down. Now what we are interested in is to calculate what is the value of the peak-to-peak voltage across the capacitor, the peak-to-peak value of the capacitor voltage, because this represents the output voltage ripple. Well, if we look at this triangle, as I mentioned, the area of this triangle represents a charge that's being injected into the output decoupling capacitor, and so it will take the output voltage from its minimum value to its maximum value. And as we know, delta V, it will take the capacitor voltage from minimum to maximum, which is delta V voltage change. We know that delta V is the Q inside this triangle divided by the capacitance C. So what is the value of Q? It's the area of the triangle. Well, the triangle is half the base, the area of a triangle is half the base times the height h. Well, the height is very simple, since we know that the capacitor current is an inductor current without its DC component. So essentially the peak-to-peak value of the capacitor current is essentially the peak-to-peak value of the inductor current. And so the height of this triangle is delta I or delta IL over 2. Now, what about the base? Well, this is a periodic function. It starts 0 here and then return back to 0 here. So all of this distance is the cycle time t. And since this triangle and this triangle are congruent, this means this distance is equal to this distance, or essentially this is equal to this. And so the base of the triangle is going to be t capital over 2, right? Essentially the triangle splits the cycle time. You have half of it here for the first positive triangle, and the negative triangle has another half t over 2. And the height is, as I mentioned, delta IL over 2. So if we simplify this, the Q will have delta IL over 8 times F, where T I brought it down to the denominator from the numerator, so it becomes as an F. And so delta V will be this expression for Q just divided by C. and that's the value of the peak-to-peak value of the output voltage ripple. Now, what is the value of delta IL from last video? Delta IL is the output voltage, the DC value of the output voltage, times 1 minus D divided by FL, the frequency times the inductance. And so if we replace this into this equation, we find that the delta V is equal to V out times 1 minus D divided by 8F square L. And this is the expression for the peak-to-peak value of the output voltage ripple. All you need to know is the output voltage, what duty cycle you are operating at, what is the frequency, and what is the inductance, as given by this equation. Obviously, if we want to reduce delta V, you can either increase C, the capacitance C, or increase the inductance L. But what we are looking for is an equation that helps us determine the value of the required C. So we're going to rearrange the terms of this equation. We'll find that we have the normalized ripple. I just brought V out to the denominator of the left side, is equal to 1 minus D divided by 8F square LC. Now you can bring C to the other side, so C is equal to 1 minus D over 8F square L delta V over V out. And then, what is the value of the peak-to-peak ripple? The ratio between the peak-to-peak ripple to its DC component, which is given by this term. Well, typically for analog and RF circuits, if you are designing a DC, a buck converter for them, you want this normalized value to be 1% or less. For digital circuit, you want it 5% or less. And then from knowing the duty cycle you are operating at, as well as the frequency and the inductance, you can find the required capacitance C that will enable you to obtain a peak-to-peak value delta V that's either 1% or 5% of the DC value of the output voltage. Okay, as given by this equation. Now, if you are designing a buck converter D with a duty cycle that's variable between 0 and 1, so you want to account for the worst case, and the worst case, as you can see, the largest capacitance will happen when D is equal to approaches 0 essentially, and so we get this equation, and when you require that C, the minimum capacitance or the output decoupling capacitance should be larger than this term. We just replace D by 0. Okay, and this is a design equation that help us determine the value of the required capacitance. Just one last note, you can notice that the output ripple, as I mentioned, you can achieve this output ripple or normalized output ripple by either increasing L or C. Either way, you will reduce delta V, but the inductor L occupies much larger volume size than the capacitor with the same amount of energy storage. And that's why my point here is the capacitors typically increasing the inductance will require a much larger volume size inductor, which increases the overall volume size of the buck converter. On the other hand, if you use a larger capacitance, that's better because capacitors are much smaller than inductors in size, as well as weight. So my point is, just use the equations that determine the value of the required inductance is the condition for continuous current, continuous conduction mode, or avoiding the negative current in a buck converter, while Cmin comes from this equation. Just increase C until you get the required peak-to-peak, normalized peak-to-peak output voltage rate. Now there is another condition or another point that we need to determine in order to select the capacitors that we are going to use in our design. So we selected C. Of course, we have RMS current rating as usual, but there is also another point related to the frequency or the self-resonance frequency of a capacitor. So the capacitance is, or the reactance of a capacitor is given by 1 over J omega C. So if we plot that versus frequency using log scale, it will be a straight line decreasing, right? And if we look at the frequency domain, if this is the load resistor of the buck, and then you have the switches here. So as we know, there is the current that's coming from the inductor. All the harmonics will flow into the capacitor, while the DC component of the inductor current will flow into the load resistor. So if we put this as R, whatever is the value, we should select C such that the fundamental component of the inductor current, or at the fundamental frequency of the inductor current, the impedance or the reactance of the capacitor 1 over J omega 1C, where omega 1 is the frequency of the fundamental component of the inductor current, is 10 times smaller, so that we can satisfy the condition that all of the harmonics will see the capacitor C as a short circuit 10 times smaller than the resistance. So basically all of the harmonics will be shunted via the output decoupling capacitor to the ground instead of flowing into the load resistor. However, that's not the point. The issue is in a capacitor, if we look at the capacitor, due to its structure as well as the printed circuit board traces, we introduce some kind of equivalent series inductance. Let's call it LS. And so as we increase the frequency, we have 1 over J omega C, and we have J omega L, and we have this is the equivalent impedance. So initially, this term, the second term, is 0, and essentially we have a capacitor. The inductance does not appear until at some self-resonance. We'll find that essentially the capacitor term, the first term become almost 0, and the second term becomes the dominant one, and essentially the capacitor behaves as an inductive reactance. And obviously we want to use the capacitor in this range because this is when it's actually capacitor. We don't want to operate above resonance. So the condition here, you will find in the data sheet the self-resonant frequency of a capacitor, and you should ensure that the rule of thumb, self-resonant, when you select a capacitor, the self-resonant frequency of the capacitor is larger than twice the fundamental frequency, this point essentially 2f, to be larger than twice the fundamental component of, or the switching frequency of the buck converter, so that we ensure at least the capacitor, the fundamental component of the inductor current, we see the capacitor as a capacitor rather than as an inductor. Generally, the larger the capacitance, the lower its self-resonance frequency, and that's why, say, if I need to use 150 microfarad output decoupling capacitors, according to, say, this equation, right, we need to use 150 microfarad. Well, 150 microfarad might have and I'm operating, say, at 500 kilohertz. We'll find that maybe its self-resonance is at, say, 600 kilohertz, so of the capacitor. So essentially, the capacitor is self-resonance frequency is not equal to twice 500 kilohertz or 1000 kilohertz in this case. No, actually it's lower, 600 kilohertz. And the reason is self-resonance is lower for larger capacitor because it's much easier for the same amount of series inductance due to the PCB traces. Larger capacitance will reduce the self-resonance frequency, which happen at 1 over square root L LSC. So if you increase C, you'll find that the self-resonance frequency is going to decrease. So what we do in this case, instead of implementing the 150 microfarad using a single capacitor, we use, say, 2 capacitors in parallel, or three capacitors in parallel. Each one is, say, 47 microfarads. And in this way, you will find that the inductance, the equivalent inductance of each capacitor appear in parallel. And so their equivalent is just LS over 3, and then you have the same capacitance C, the 150 or whatever, 3 times 47 farad. Okay, so the point here is when you use multiple capacitors and connect them in parallel, their inductances, their parasitic inductances appear in parallel, so they essentially decrease by the factor of number of capacitors that you are connecting in parallel. Okay. Now there is also another factor to consider, which is the capacitor is not only has a series inductance, it also has an equivalent series resistance. And so at this point, the resonance self-resonance frequency, that's when the capacitance cancels the inductance, and the impedance, the equivalent impedance of the capacitor is just a resistor Rs. And this resistor, since the harmonic currents or the current of the capacitor is basically the harmonic components of the inductor current, flows into the capacitor in series with the resistor. So the resistor, not only the capacitor is going to introduce delta V, peak to peak voltage ripple in the output voltage, but its series resistance will add to that ripple. So obviously the peak to peak value of the ripple due to the ESR of the capacitor will equal to the capacitor current multiplied by the resistance Rs. And the capacitor current, the peak to peak value of the capacitor current is delta I. So delta V ESR is equal to delta IL times Rs. Delta IL is basically the output voltage times 1 minus D divided by FL, and then this one is multiplied by Rs. And then we can bring V out to the other side as shown here. We have the normalized value, and then we have Rs divided by FL. So essentially it's as if we are dividing the equivalent series resistance of the capacitor by the impedance of the inductors FL, of course without the 2 pi, and then we have 1 minus D. And as you can see, the worst case for the largest ripple will happen when the duty cycle is approaching 0. And so essentially the worst case ripple essentially will be, due to the equivalent series resistance, will be Rs over FL. Now we have a ripple component due to the resistor, the equivalent series resistor of the capacitor, as well as a ripple component due to the capacitance itself of the capacitor. So how do we combine them? What will be the total ripple delta V? There is a simple expression, and which is the norm of the ripple due to the ESR square plus the ripple due to the capacitor square. And the norm is, because the ripple in the resistor due to the capacitor current will be in phase with the capacitor current, which is the inductor ripple current, right? While the ripple in the capacitor voltage will be 90 degrees phase shifted. That's why to combine them we just use the norm essentially. And then one last point, as I mentioned, the DC current, the inductor current has a DC that flows in the node resistor, while all of the ripple, assuming the capacitance is very small, flows into the decoupling capacitor. And so if we represent the inductor current using a Fourier series as a DC component plus higher order harmonics, we'll find that this component flows and sees all of these. And that's what I did here. All of the harmonics will see the impedance due to the equivalent series resistance of the capacitor, its series inductance, and its actual capacitance, while the DC component sees the load resistor, and so the output in Fourier series is given by this expression.